All right, one thing I forgot to touch on in this last problem, and it's because it didn't exist, is if you look at the original problem, it was 2x squared over x squared minus 1. The power of the numerator was exactly the same as the denominator, so there were no slant asymptotes on this one for us to worry about. The next problem, as you can see, we have y equals x cubed over x squared plus 1. This one is going to have a slant asymptote because the numerator's power is exactly 1 higher than the denominator. So we still need to get all the other information. So we're going to talk about our domain. Well, let's see. The domain, anything can be plugged into the numerator. X squared plus 1 is never going to equal 0, so the domain here is all real numbers, which is kind of nice. There's no domain restrictions. We need the x and y intercepts. All right, the y-intercept is the easier when you simply plug 0 in for x. If you plug 0 in for x, you're going to get out 0. The x-intercept is when you take that function and set it equal to 0. If I set that equal to 0, the way to make it 0 is the numerator to be 0, so the only value there would be x. Again, it makes sense that you're going to have something potentially at the origin. Obviously, we can have them where we have different x and y intercepts, but in this case, these last two cases, it worked out the same. Okay, vertical asymptotes. Vertical asymptotes are what makes the denominator 0. We've already talked about that. There's no domain restrictions, so there are none. Horizontal asymptotes. Horizontal asymptote is the limit of that function as x approaches positive or negative infinity. The numerator grows at a faster rate than the denominator does in this case, so there are no horizontal asymptotes. And just an FYI, if you have a slant asymptote, you will never have a horizontal asymptote again because the degree is always 1 higher on the top than it is on the bottom. So you can never have a horizontal and a slant asymptote. You can have a vertical and a slant asymptote, but just never a horizontal and slant at the same time. All right, to find the slant asymptote, here's what you have to do. We're going to have to go back to some long division of polynomials. So hopefully you guys remember how to do this. If not, hopefully this is going to come back to you relatively quickly. So to find my slant asymptote, you must do long division of polynomials, which means I need to divide x cubed by x squared plus 1. So what goes underneath of here is x cubed. And I need to divide it by x squared plus 1. Well, the thing about dividing polynomials is you must have a placeholder for all of your degrees of your polynomial all the way down to your constants. So because I just have x cubed, I have to add a 0x squared, a 0x, and a 0. Got to have a placeholder. Also have to have a placeholder for this stuff on the outside that we're dividing by. So x squared plus 1 needs to be written as x squared plus 0x plus 1. Got to have that placeholder for the x term. All right, to do long division, this is what we're looking at. If you don't remember how to do this, this is what you're thinking. Look at your first term here. You need to ask yourself, what do I multiply by that first term to get that term? Well, I'd have to multiply the x squared by x. And when you do that, the term goes on top of the appropriate place, which is your x spot. And then you're going to take that x and you're going to multiply it by all three terms on the outside. So that gives us x cubed, 0x squared, plus x. That's distributing the x to all of that. Okay? I'm going to erase that little line there. Oops, one more. All right, and then, long division, we subtract. So we get x cubed minus x cubed. That has to go away. The first term must go away. That's the purpose of doing this. Then we get 0x squared minus 0x squared, still 0x squared. And because that should be the next term, I'll write that down. And then I've got 0x minus x, which is just going to be negative x. And then technically you would bring down the next term. Here's the good news. If I take a cubic function, which is what we started with, and I divide it by a quadratic function, I'm taking something which is cubic, something to the power of 3, dividing it by something to the power of 2, I should get something to the power of 1. Well, I have that already. Let's see what happens now. What would I have to multiply x squared by to get 0x squared? 0, right? So really what we have is this is our remainder. Now you don't need this part, you don't need this part. We just bring those down if you actually have to do more. But our remainder is negative x. So technically what we get out of this by doing long division is this equation. Y equals x minus x over x squared plus 1. But here's the good thing. When you're dealing with a slant asymptote, the remainder doesn't mean anything. We can get rid of it. So my slant asymptote simply has the equation y equals x. So over here, my slant asymptote is the equation y equals x, which is definitely not a vertical or a horizontal asymptote. It is a slanted asymptote. It has a slope to it. Okay, now we get to go back to the calculus. Now we get to do the derivatives, find our increasing, decreasing, all that kind of good stuff. So, try and run through these here with you guys. Slightly faster pace. So, first derivative. Derivative of the top times the bottom minus derivative of the bottom times the top all over bottom squared. Simplifying, 3x to the 4th plus 3x squared minus, what is that, 2x to the 4th? Did I write that right? Yeah, 2x to the 4th over x squared plus 1 squared. Still simplifying because I want to be able to deal with this easily. 3x to the 4th minus 2x to the 4th just gives me an x to the 4th minus 3x squared all over x squared plus 1 squared. All right, we got to set that equal to 0. In this case, again, the denominator is never going to equal 0, so it's not going to have an undefined slope anywhere. Set the numerator equal to 0. And solve. So we're going to have to factor out an x squared, which leaves x squared minus 3. So either x is going to be 0 from this one, or using this one, x squared has to be 3, which means x has to be the plus or minus root 3. Nope, I made a mistake somewhere. Where did I make my mistake? Ah, that should be plus. Hopefully some of you guys caught that. That makes a big difference. Let's try this over again. So that's going to be x squared factored out and then x squared plus 3. I was going to say, I didn't think we had that many critical values. So really only x equals 0 because x squared plus 3 isn't going to make any difference. So my only critical value is at 0. Let's test around it. If I plug a negative value, again, I'm going to go with the most simplified version that I can, which is this one. Well, the interesting thing about this is the numerator is x to the 4th, even power, plus 3x squared, even power. If I plug anything in, the whole numerator is positive. But then look at your denominator. The denominator is something plus 1 squared, which is going to be another positive value. So it really doesn't make any difference what I plug in. The entire thing is increasing. Okay, that's kind of interesting in itself. All right, which tells me that there's no local max, no local min. So over here on the side, let's just write this out real quick. So this is going to be increasing. It is increasing on the interval from negative infinity to 0 and union with 0 to infinity. Sorry, bell just rang, so you might hear some announcements in the background. Okay, so increasing on the entire thing except at 0 where the slope is actually 0. So you can't include 0 because it's not increasing on the entire thing. No local, try and spell that right, max or min. Okay, it never changes direction. All right, so let's look at the second derivative, which once again is going to come from the easier form. So f double prime is going to be, let's see, the derivative of the top, 4x cubed plus 6x times the bottom, x squared plus 1 squared, minus the derivative of the bottom, chain rule, 2x squared plus 1 times derivative of the inside, 2x, times the top, x to the fourth, plus 3x squared, all that mess over the denominator, x squared plus 1 to the fourth. Whew, what a mess. But again, just like we did before, we actually have x squared plus 1 in common in everything. So I can get rid of that one, get rid of one of those, which is going to give me a 3 there. Still going to have to FOIL, it looks like, on the numerator here in order to simplify. All right, so let's go ahead and do it. It's not the worst. So foiling these two. Okay, what is that going to be? 4x to the fifth. Outside is going to give me 4x cubed. Inside is going to give me 6x cubed, so that's going to add to 10x cubed. And then plus 6x. That's the foiling of the first part. Now we got to distribute the -2, the 2x into here. So that's going to be distributing a -4x. So we should get minus 4x to the fifth. That's nice. And then we should get a minus 12x cubed over x squared plus 1 cubed. So one of the nice things is I see the 4x to the fifth, and that 4x to the fifth are going to go away. I can combine the 2x cubed terms, so I'm going to get a, what is that going to be, minus 2x cubed plus 6x on top over x squared plus 1 cubed. And again, we're looking for where this is equal to 0. It's much easier to deal with now. Okay, the denominator will never be 0. It's x squared plus 1. I don't care that I'm cubing it. It's x squared plus 1. That cannot be 0, so it's really the numerator. So we can factor a, looks like a -2x out. -2x, leaving us with x squared plus, nope, minus this time. This time I actually do have x squared minus 3. So x is either going to equal 0. This time you would have x squared equaling 3, or x equals plus or minus square root of 3. At that time we actually do have to worry about it. All right, let's create our number line for our second derivative. I'm going to have to put on here -√3, 0, and +√3. Now let's test values around that. Remember, we're going to go into the second derivative. Remember that the denominator is always positive. So I'm really only going to test in here, which is going to be much easier to deal with. -√3, that's about -1.7. Again, this is a value you should probably know the approximation of. So something left of that would be -2. If I plug -2 in, you're going to get a positive here. Plugging -2 in is going to give you 4 minus 3. That's positive here. So two positives is going to make a positive, which means concave up. All right, in between -1.7 or so and 0 will be like -1. Plug a negative in outside here, that's positive. Plug -1 inside, you're going to get negative. So that's going to be concave down. Plugging in +1, which is in between 0 and √3, it's going to be negative on the outside, negative on the inside, so that's going to be positive, so concave up. And then plugging in something greater than the square root of 3, like 2, is going to be negative on the outside, positive on the inside, so that's negative, concave down. All right, this time, all of these values, negative root 3, 0, and root 3, are all on the original graph because it's not undefined anywhere, so these are all going to give us inflection points. So I'm going to have 3 inflection points. The first one will be at negative root 3 something. The next one will be at 0 something. And then the last one is going to be at positive root 3 something. I already know the 0 one because we figured that out. That's the origin. So that's going to be at 0, 0. If you plug in 0 for x, you're going to get 0 for y. Plugging in negative root 3 back into the original function. That's going to be a little more ugly. So if we plug in, see, x cubed over x squared plus 1. So x cubed, y equals negative root 3 cubed over root 3 squared plus 1. Well, so the denominator is the easy part. Root 3 squared is 3. So that's going to give us 4 in the denominator. And then negative root 3 cubed is root 3 times root 3 times root 3, but it will be negative. So that's going to be negative 3 root 3, multiplying all those together. So I get negative 3 root 3 over 4. Looks like plugging in the positive square root of 3 is going to be exactly the same thing, except on top it's going to be positive instead of negative. So that's going to give us 3 root 3 over 4. Those are ugly inflection points, but those are the inflection points in the graph. Those are not going to be easy to locate, but kind of try and see where they are when we get to the graph. All right, we've got all the information that we need now. We've got our intervals of concavity, we've got our inflection points, we've got increasing, decreasing. There are no local maxes and local mins. So let's go ahead and look at what this thing looks like on a graph. And we do have a slant asymptote to deal with. All right, we're almost done. Okay, first thing I'm going to say is we know that we have a point at 0, 0. I also know that I have a slant asymptote, which is y equals x, which goes right through the origin. That's your 45-degree line. Y equals x. So that's my slant asymptote. You can cross a slant asymptote again towards the middle. A slant asymptote is really only an asymptote as the function starts to get really far away from the origin. So towards the extremes. Well, here's the idea. I'm going to need to plot those inflection points because without those, I'm not going to know what the heck is going on this graph. So my inflection points, I have one at 0, 0, so I've got one there. I've also got one at positive root 3, positive 3 square root of 3 over 4. So positive root 3 is about 1.7. 3 square root of 3 over 4, probably go ahead and plug that into your calculator just to get a general sense, but you're talking about 3 times 1.7, which is about 5.1, divided by 4. It's a little bigger than 1 1/4. So you're talking about 1.7, which is maybe about here, here, and then 1 1/4 maybe about right here. It's going to be below the slant asymptote. That's my first inflection point. The second one should be the mirror image of it. It's going to be negative. Let me move this up so I can actually try and draw it. Negative root 3, negative whatever that value was. It should be right about here. Should be the exact opposite. And that's just using some estimation techniques. We know that the function is increasing on the entire interval. It's always going up from left to right. We also know, let's go back to the concavity. It's concave up until we get to the negative square root of 3, which is at the inflection point. So in order for me to have something which is increasing and concave up, but also involving the slant asymptote, it must look something like this. That's increasing, increasing, increasing. It doesn't look concave up, but it is. And it's concave up until it hits that point. Because don't forget, as you go down towards the slant asymptote, it's still actually moving more towards the slant asymptote. So technically it is still concave up, it just doesn't look like it there. Then from that inflection point to the next inflection point, according to this, it's concave down. So now, still increasing, but concave down. It's got to look something like this until it gets there. When it gets there, it actually has a slope of 0. So it levels out right there for that one point. And then, according to the second derivative, still increasing, except for at that one point, but now concave up again, up until it gets to the next inflection point. So it'll look like this. And then it's got to be concave down for the rest of it, but still increasing. So now it's got to look like this. That should be connected. So that's actually what that graph looks like. And if you haven't already done so, go ahead and plug that into your calculator, and you would see that that's generally what the graph looks like. You might have to zoom in a little bit to the center to see that shape appear the way it does. Kind of interesting looking function. But there you go. There's one with a slant asymptote. All right, you guys should have everything that you need to complete the worksheet.